Okay, this lecture covers Chapter 11 in EE213's book, and this is about AC power. So there are a lot of jobs for electrical engineers in the power distribution, so power company, and all of that is AC power. You know, have a picture down here. This chapter really covers the concept of power, and all the three main concepts that you have to get across in this chapter are the concept of instantaneous power, average power, and RMS or effective power. And they're all related because power is still current times voltage. One of them is instant and one of them is average, and one of them is a calculation that you make. And then as a secondary part, we'll also talk about true power, apparent power, and reactive power. So instantaneous power is just like the name sounds, it's at that instant in time. So if you have some circuit, I have a circuit here, sinusoidal source is putting out current, it's putting out voltage. The current and voltage may not be in phase with each other. And if you multiply at a particular instant in time, current times voltage, you will get power in watts. So current times voltage will be power in watts, and it will be instantaneous. This is the plot out of the textbook, and it shows some power, and it has a definition, a few of their terms that we have to actually pay attention to. This Vm and Im are peak values, so Vm in your textbook is like V peak. And then V and I are still current, but they have these maximum values, and they have a period here on this plot. This plot by itself wasn't very informative, so I think it was better to break it down. But instantaneous power is a power at a particular point in time that results from I times T. So let's get my next plot. So I actually decided that it was probably more informative to break that down and show you exactly what happens. So we have a voltage that's a function of time right here, current that's a function of time right here, and notice that they each have their own phase angle. And we know how to write this in phasor notation as well. And so power by definition is voltage times current, and so if you just multiply these two trig functions together, you'll have to use a trig identity right here, and in the end you will multiply them together and you'll end up with a part right here that it's actually a DC component. There's no sinusoid left there anymore, and then you have this part right here which results from that's trig identity, but this is running at twice the frequency. So I plotted it out. I used MATLAB. I have a voltage function right here, which is cosine. I made the frequency be 1 hertz because it was easy. So I said 2 pi 1 hertz times t. It's 2 pi ft is that argument of the cosine function. And then I made I had to call it II because I is a complex number or imaginary number in MATLAB. And I said II was cosine 2 pi ft plus a phase angle right there is 0.8 radians, and then power is voltage times current, and then I plot them all. So what I have in my plot right here, the blue line is voltage as a function of time, and then my red line is current as a function of time, and there was a phase difference there of 0.8 radians. In other words, current is leading voltage by 0.8 radians in this example. Because why? Because current occurs before voltage occurs, so its current is leading there. And then I multiply point by point voltage times current at each one of these points, and I plot the result right here. So there's my power. And although we can do it from a trig identity right here, what we see is that voltage is oscillating between amplitude of +1 to -1, and it actually has an average of 0. If you look at that and you average up over one period, the average is going to be 0. Current also has an average of 0. If you average up all the values of current over one period, the average will be 0 by definition of the word average. But when you multiply the two together, which is the golden plot right here, the average, which is right here, the average of this sinusoid is not 0. So that's this term right here. And so we can see it mathematically, and plotting it, we can see that that's what happens. So in your book, that's what this figure is trying to show you, that mathematically when you multiply voltage as a function of time times current as a function of time, the instantaneous value of the power will not be 0. And so my golden plot here is the instantaneous power. So instantaneous power is at a particular point of time, but average power is the average of the instantaneous power over one period. So I have here just that mathematical definition of an average. So you just integrate over one period the power and divide by the period. So you get an average value of the power. It's still in watts. Power is in watts. And as we saw when we did the trig function on the previous slide, that average power will equate to this value if written using trigonometrically, where, paying attention here, these are maximum or peak voltage and peak current. And this factor of 1/2 comes from using the trig identity here, cosine A times cosine B, you end up with a 1/2. That's actually where the 1/2 comes into play. That's why the 1/2 is there. It's not because of the amplitude. It's not related to the amplitude. It's related to what happens trigonometrically. This one factor of 1/2 will come into play. So average power is the average of the instantaneous power over one period. We calculated that. This is what that is trigonometrically. And then we can go back when we're analyzing these circuits, and we've been using phasor notation, which is a complex number. We can also note that if we are going to multiply a phasor for voltage times a phasor for current, that in phasor notation it's written this way, which is using our Euler's identity, we get this part, and then if you take the real part, you come back to the actual answer. So actually the point is the real answer is real numbers. The real answer is not a complex number. Phasor notation is a way for us to keep track of phases, but in the end, if we want a real answer, we have to take the real part. So power average is 1/2 the real part of a complex number that represents voltage times the complex number that represents current, but you have to take the complex conjugate of it. You can't multiply two complex numbers together and get the correct answer. You have to multiply one times the complex conjugate of the other so that you get the real answer. And this value will equal this value, the actual real trig answer. And I did have a little example to show you that. That also brings up a point here that average power is 1/2 VMIM, which instantaneously, or which is also I squared R. So power is voltage times current. It's also I squared R. It's also V squared over R. But I squared, again, if you're doing the phasor notation, you cannot just multiply the two complex numbers together. I squared, or magnitude of I squared, has to be I times I complex conjugate. Book has a good example. I think it's example 11.1. It says the instantaneous power is given by, so instantaneous is at a particular instant of time, so I expect this to be a function of time, and I can't do my phasor notation as a function of time, right? So this is truly what's really happening. It's really a function of time. So I have a cosine of a voltage. I have a cosine function representing the voltage and a cosine function representing the current in the circuit, and they have different phases relative to each other, which is exactly what happens. So you apply the trig identity to this cosine A times cosine B, and you'll get this answer right here. Notice that I have a part that's running at twice the frequency. The original circuit is running at 377 radians per second. It's now, when I multiply the two together instantaneously, I have something that's running at twice the frequency plus this cosine term multiplied by 600. So redoing that math right there, multiplying it out, I get the power instantaneously is 344 plus this part running at twice the frequency. So the average power is this DC term right here, and the instantaneous part is the DC term plus the AC portion running at twice the frequency. I can apply their formula, the trig formula that we can derive, and say that the average power is 1/2 voltage max current max times the cosine of the angular difference between the two signals. If I do that math, multiply it out the formula, I get this answer, which is exactly the 344.2 watts, which is the DC part of this equation right here. So it does check. The DC part is given by this part of the multiplying the two cosine functions together. So that gives you the DC part. DC part is right here, and the part running at twice the frequency is right there, which you need if you want instantaneous power. So these check. Now the other part is we could have taken these two cosine functions right from the beginning, and we could have represented them in phasor notation and seen that we go through the process of getting the exact same answer, which I think is worthwhile to do. So I will go ahead and do that here. So here's the two actual real world signals right here. And so we want to convert now to our convenient notation of phasor notation, just so that I can show you that it works out the same. So if we had some circuit and we had analyzed voltage and current and we had the answer in phasors, I want to show you that you can still calculate from your phasor notation the average power that's needed. So I'm going to say voltage now is 1200. In phasor notation, we would say that it's cosine 45 degrees plus J sine 45 degrees, which I already multiplied that out, is 848.5 plus J, same thing, 848.5. That's voltage, assume it's in volts. Current, actually I should make these capital bold V's and bold I's now because I'm in phasor notation. Book has it in bold. Oops. Book has it in bold. I guess I can't do that. It's hard to do it in bold when you're handwriting it, so a lot of times we just put a vector symbol over it. So I vector symbol. And so this has already been multiplied together right here. So I'm just going to say its amplitude right here is 1. So 1 cosine minus 10 plus J sine minus 10. And that'll equal 0.9848 plus J 0.1736. So now I have it in our phasor notation, and so if I wanted to find the average power, it's 1/2. Remember, our 1/2 actually comes in from multiplying cosine A cosine B. 1/2 the real part of voltage, which is in phasor notation, so I'll put the little vector symbol over it, times current in phasor notation, complex conjugate. So if we do that math, multiplying these two phasors together, our answer will be, I'm going to pause it and calculate. Oh, and I see a little mistake. This is a minus sign right here. Let me fix that real quick. That should be a minus sign. Minus, because it's minus 10 degrees, right? Minus 10. Okay, so when I multiply these two complex numbers together, V times I complex conjugate, I will get 344 plus I 491, or J because we're engineers. So I want the real part of that. So real part of that, which is 344 watts. So you can see that if I had done the problem from my phasor notation right from the start, preserving all the complex numbers that represent the phases, my actual real average power in the end is the real part of multiplying voltage and current phasors together. So it comes out with the same answer. So what we got so far is we understand where instantaneous power comes from, which is instantaneous at an instant in time voltage times current. And we understand where average power comes from, and that's the multiplying together of the voltage times the current. Both of them are instantaneous values, which will result in a sinusoidal function running at twice the radian frequency and having a DC offset value. And the DC offset value right here is the average power. Okay, so that's the first two concepts to get out of this chapter. And of course your chapter likes to mix up, likes to do a lot of mixing up of doing something in a angular representation, a trigonometric representation, or a complex number representation. Your textbook just enjoys mixing all of these things up for some reason. So for example, 11.2 gives you the impedance of a circuit, and it gives it to you in a complex value, and it tells you the voltage source is something, and it gives it to you in the angular representation. So if you want to do this problem, you have to make everybody the same. So you have to find power. So power is current times voltage. So if we have V and Z, we can find I. So you can't mix up the angular and the complex notation. You have to convert them to be of the same type. I don't care whether it's you convert them all to be complex numbers or you convert them all to be angles. In this case, they converted them all to be angles. So you got your current out of that, and then apply the formula for the average power using just the angles. In this case, I think it was easier to do it in the angular representation. So, and then you get the answer. So another problem, your similar problem here has this circuit. Now, one of the little tricks of this circuit is that a resistor will absorb power or dissipate power. It absorbs the power and dissipates it as heat, but a capacitor will not. It's just a energy storage device. But anyway, so you have to analyze this circuit using all your Ohm's law, and you find out that the current is voltage divided by the total impedance. Well, the total impedance is 4 minus J2. They're in series. You just add them up. Again, now I have this mixed angular notation and complex number notation, so I have to convert it. Easier to do it in angles instead of complex numbers in this case, but for some reason I tend to gravitate towards complex numbers. Apply it, you get the average power. Okay, so apply the formula, get the average power. the trick is current through the resistor right now, well, it's one current total. No matter how you look at it, there's only one current in the circuit. So I find my one current, and that's also the current through the resistor. And the voltage across it is I times R. So it's still in phase. The phase doesn't change when it's a resistor. Does my pen write on here? No, my pen doesn't write on here. I wanted my pen to write. Okay, so the phase didn't change because the current and voltage are in phase in a resistor, and so then you can calculate the power absorbed by the resistor. There is no power absorbed by the capacitor, so do not say I times minus JXC or I times minus J2 and calculate power absorbed by the resistor, because there is no power absorbed by the capacitor. There will be no power absorbed by the capacitor. So, and then the other part of your textbook is just making these problems bigger and more complicated. So now I can have to apply my normal mesh analysis to this circuit and keep track of whether I have things in a complex representation or an angular representation, find currents, find voltages in the loop. But again, the thing to remember that I can find a total impedance, and I can calculate then a total power dissipated by the circuit, but the components that are dissipating the power are the resistive components. The inductor and the capacitor do not dissipate any power. So moving on to section 11.3, the maximum average power transfer. They do said average in here. Okay, so I have to note that it's average. So if you just think of a generic model for a circuit, you have the source side and then you have some load attached to it. So ZL means the load impedance, and Z meaning it could be something with capacitors and inductors in it versus a resistor. So this source side, you can convert it to its Thevenin equivalent. So I have a V Thevenin and a Z Thevenin. And so if you recall from a resistor circuit, when we were doing purely resistor circuits, you had maximum power transfer when R Thevenin equals R load. And how we found that, I'm going to run through that again real quick, how we found that. And the exact same thing is going to apply when we're doing Z's instead of R's. The only difference is that there's going to be a complex conjugate of Z involved, because when we're dealing with power, we end up having voltage times current complex conjugate. So let's just refresh your memory on doing it with a resistive circuit. If this was a resistor here, R load, and R Thevenin, which I can also just call the resistance of the source, our source. How is it that we proved that maximum power transfer to the load occurs when the source resistance or impedance equals the load resistance or impedance? And this is actually an important concept, because this is a concept of impedance matching. You match the impedance of your source to the impedance of your load because you want to transfer the max amount of power possible to the load. This is an especially important concept in RF concepts, where you're dealing with antennas and cabling, and you have to match the impedance of your cable to the impedance of your antenna, because you want your antenna to transfer maximum power to and from the cable that connects to the antenna. So it's actually a really important application. Let's just recall what it would be if we had a resistor circuit. So if we had a resistor circuit, we would have something like a V source, which could be AC, and then our R source, and then our R load over here. And the current in this loop, I, is the V source over Rs plus Rl, which is just our Ohm's law like we've always done. But I'm going to just prove that this is when maximum power transfer occurs. Well, Rs equals Rl for max power in RL. So it turns out if I were to vary RL, if I was to change the value of RL and I were to calculate the power in the load, it would do some kind of a plot like this. Something like that. And there would be a point where you had maximum power in the load, and that point would be when Rs and RL were equal. So if you want to prove when that power is maximum, you need an equation that describes the power in the load, and you find a derivative of that and you set it equal to 0, because when the derivative is equal to 0, the slope of that is 0. So that's the general proof that you have to take. So I is V source over Rs plus RL, and then power in the load is I squared RL. So substituting that in, you would have V squared over Rs plus RL squared times RL. So that's power in the load, and what we're interested in is that the derivative of power in the load with respect to the load resistor equals 0. So this is a plot of the load resistor versus power in the load, and we're interested in when the derivative of this curve, represented right here, the derivative of that curve is equal to 0. I'm going to change my pen a little bit because it's too thick. So we have to find dRL of V squared RL divided by Rs plus RL squared, and set that equal to 0. Continuing on, we have that is V squared comes out in front of the derivative operator, and then we have, I'm going to do it, but derivative of the first times the second, and derivative of the second times the first. So my first term is the RL. So derivative of RL is 1 times the second term, which is 1 over Rs plus RL squared, plus the derivative of the second, which is the derivative of this 1 over Rs plus RL squared, which will be minus 2 Rs plus RL to the minus 3 power times RL, and you set that equal to 0. So the V squareds go away. I do a little algebra, and I have 1 over Rs plus RL squared equals 2RL over Rs plus RL cubed, and manipulate this a little bit more. I don't have to go through the algebra, but what you'll end up is that Rs equals RL. So truly I can just prove that when the load resistor equals the source resistor, then we have maximum power transfer, because that's where the derivative of the curve equals 0. And so that's all fine and good. Now that maximum power transfer is, so P at max is then I squared RL, and since I is this value, but Rs and RL are equal, that's V squared over 2R, I'll just say R squared times R. They're both L's. So that ends up being V squared over 4RL. That's when the maximum power transfer occurs. So Ku'ali'i, I think you have a question about why is there an 8 in the denominator, and I'm going to show you why there's an 8 in the denominator. So this is an instantaneous equation. So V, if you're doing power equations, you can do them with, we haven't talked about the RMS section, but V RMS is 1 over square root of 2 V peak. This is the thing that you measure. VRMS is what you measure with your power meter, and VRMS is also what you have to use when you do power calculations. Otherwise you have to pay attention to the 1/2 and the things like that for averages. But if we substitute in that VRMS is 1 over root 2 V peak, and we substitute that back into this equation, then we have that P max equals 1 over root 2 V peak squared over 4RL, which ends up being V peak squared over 8RL. And that explains where the 8 comes from in your textbook. Now, the thing that's different about what's in your textbook versus what I just did with real resistors is the fact that they're doing everything with reactances or impedances. So I'm going to bring your textbook over here for a minute. So they go through the same process. You have the load impedance here, the source impedance and the load impedance, and then you have to find current through the load. So it looks like our voltage divided by R source plus RL, only now it's voltage divided by Z Thevenin and Z load. And so we break that up into real and imaginary parts right here. Average power to the load, we know, is this equation right here. And it's switched now to phasor notation, so remember that magnitude of I squared is I times I complex conjugate. So you go through the math right there. And we want to find, they treated the real parts and the imaginary parts separately. So they treated the resistance R and the reactance X separately. And so, but again, you have to find the derivative with respect to XL, or the derivative of the power with respect to the load resistance, and find when they equal 0. So it turns out that on the reactance part, this derivative will equal 0 when XL equals minus X Thevenin. So when the load reactance equals the conjugate of the source or the Thevenin reactance. And then on the resistor part, it actually comes out the same as a resistive circuit. So when R Thevenin equals R load, then the derivative of the power goes to 0. So using those two parts, the real and the imaginary part, or the real and the reactive parts, you find out that when Z load equals R load plus JX load, when that equals the conjugate of the source impedance or the Thevenin impedance, that's when you have maximum power transfer. So the only difference between this and doing it with a resistor circuit is that you have to worry about there being complex conjugates. And then your book didn't explain where the 8 was, but the 8 comes from the fact that when you are doing something in phasor notation, those are peak values. And it didn't explain where RMS was coming from, because the next section is the RMS section. So I will show you again where that 8 is coming from. So Okay, so the example out of the textbook, you have this circuit here, and part of what your author likes to do is mix up. Again, the author likes to mix up representing numbers with complex phasor notation and representing numbers with angles. 10 at an angle of 0 is just a 10 with no imaginary part. So on the solution to this problem, you first have to obtain the Thevenin equivalent of the source, which would be everything to the left of where Z load is attached. So the added complexity of doing this problem is just that you have to find that Z Thevenin first. So we'll just go through it as a refresher. So when you find the Z Thevenin, the first thing you do is either short the voltage source out or open up a current source if it's in there. So here the voltage source is shorted out, and then you can see that the 4 ohms is in parallel with 8 minus J6. So those two are in parallel, and then you add the 5J in, and then you can have the total equivalent impedance as seen by the load here. So that's what they did here. They have the J5 that's in series with the 4 that's in parallel with 8 minus 6J. So they have it here. You can just crunch through the numbers and you'll get that as the equivalent impedance. One thing that I thought was confusing about this problem is that whenever you see reactances written as J5 or minus J6, that's because you are in an AC circuit and not a DC circuit, and so at some particular frequency the reactance is J5 and minus J6, but that is at a particular frequency for this circuit, and we must not forget that this circuit is an AC circuit, and yet the author drew a DC thing here. So if DC was really, a DC source was really in this circuit, the inductor would be a short and the capacitor would be an open circuit charged up to 10 volts. So warning, warning, that is an AC source at 10 volts peak, 10 volts peak AC source running at some frequency, and we don't know what that frequency is right now. So don't let that confusion part of the circuit throw you off. So to find the V Thevenin, is the voltage at the terminals, the V Thevenin terminals with the source put back in the circuit. So you can treat that sort of as a voltage divider, and you can find what the voltage is at these terminals with the voltage source, which is an AC voltage source, put back into the circuit. So then now I have V Thevenin and I have R Thevenin or Z Thevenin, and Z load has to be Z Thevenin complex conjugate. That's when the maximum power transfer occurs. And when you plug into this formula for what the P maximum is, the one thing you have to do is that you have to say V Thevenin, magnitude of V Thevenin squared is this number times its complex conjugate. And when you do that, you don't have an imaginary part. And then, yes, and then it shows it divided by R Thevenin. Not Z Thevenin, R Thevenin, because power is dissipated by the resistive part of the circuit and not any inductive part of or capacitive part of the circuit. So I think there's, in some ways, there's steps left out in this example problem. But that's when the maximum power transfer occurs. It doesn't occur, power is not dissipated or used up by the load for the reactive part of the load, only for the resistive part of the load. So that's why there's a resistor in the denominator. So now let's talk about this effective or RMS value. The book gives this definition. Effective value, well, first of all, I didn't like what they said, which is like it says at the beginning of the chapter, the idea of effective value arises from the need to measure the effectiveness of a voltage or current source delivering power to a resistive load. So since when is it permissible to say the definition of effective is something that's effective? That's what the textbook is saying to me. But anyway, so what it really means is it's taking an AC circuit and saying how much power is given to a resistive load and saying what is that equivalent to in the DC world. So let me show you what I mean by that. So let me get my pen. If I have a resistor circuit, and it's an AC source, 1K ohm, 10 volts, and I'm running 10 volts peak right there, and if I calculate the power dissipated by this load, well, I can tell right now that the current is I is 10 volts peak divided by 1K ohm, which is going to be 10 milliamps peak. So this is peak values, right? But so if I do instantaneous values for current, power equals voltage times current. Let's make it I of t times V of t. Instantaneous values. Instantaneous. My power instantaneous is 10 milliamps times times 10 volts, voltage times current times, and they're in phase, right? Cosine squared omega t. So it's 10 milliamps cosine omega t times 10 volts cosine omega t. So that's cosine squared omega t. You end up with using the trig identity. Cosine A times cosine B equals cosine A plus B, 1/2 cosine A plus B plus 1/2 cosine A minus B. So we apply that trig identity and we get 100 milliwatts, and it's 1/2 plus 1/2 cosine 2 omega t. And so we get this power dissipated in the resistor of being 50 milliwatts. And I'm sorry, that's not instantaneous. That's actually average, right? That's instantaneous, and it's left as a function of time. Well, this is the instantaneous portion. This is instantaneous, and then this portion right here is the DC portion, or the average. Yeah, so I correct that there for a moment. So now what DC circuit would dissipate at exactly the same amount of power? So I have some DC source right here and my 1K ohm resistor, and I want P to equal voltage times current times voltage, and I want it to equal 50 milliwatts. Let's see, let's do I want it voltage times current exactly. So so we want current times voltage to equal 50 milliwatts in this DC circuit. So we want the same 50 milliwatts power dissipated in this DC circuit as a 1K ohm running at 10 volts peak, dissipating 50 milliwatts average in this AC circuit. So power also equals V squared over R. equals 50 milliwatts, and R is 1 k ohm, so it ends up that V squared is 1000 ohms times 0.05 watts. So V squared equals 50, V equals 7.07 volts. It's actually square root of 2 times 5. So at 7.07 volts DC, I will dissipate exactly 50 milliwatts average power in this resistor, which is 10 times 1 over the square root of 2, or actually, remember that VRMS equals 1 over square root of 2 V peak. So the point is that a 10 volt peak AC signal, which is 7.07 volts RMS, will dissipate 50 milliwatts of power, and that's exactly the same as a 7.07 volt DC circuit dissipating 50 milliwatts of power. So 10 volt peak effectively dissipates the same amount of power as a 7.07 volt DC circuit dissipating 50 milliwatts of power. So that's where the effective word comes into. The RMS is a way to calculate what that, the root mean square function is a way to calculate what that effective value is. So 10 volts peak is effectively 7.07 volts RMS, and a 7.07 volt DC signal will dissipate the exact same amount of power as a 7.07 volt RMS circuit will dissipate. That's where the effective definition comes into play. So how you calculate the RMS, which means root mean square, here it's done for voltage. It could be for current, or it could be for anything that you want to find the root mean square of. It says this indicates that the effective value, or RMS, is the root, there's a square root sign, right, of the mean, which is the average, of the square of the periodic symbol. So in this case, voltage is a periodic symbol. We are going to square it. We are going to take the average of it over a period, and then we're going to take the square root of it. That's why the effective value is often known as the root mean square. So looking at what that would happen in a periodic signal. So if I have a periodic voltage signal, it looks like that, usually centered about 0. That's volts, that's time. So the first thing you want to do is, so that's a cosine omega t. The first thing you want to do is square the function. So it's going to be a cosine squared omega t. Just looking at it and squaring it value by value, you can see we're going to get something like this, right? That's what the squaring it will do, just looking at it. And what does that, so that's what it looks like when I square it. Then I'm going to take the average of it. So I'm literally going to do an average over one period. This is one period of it. Take the average of it, whatever that value comes out to be. That comes out to be some numerical scalar value. And then I'm going to take the square root of it, and that will equal the RMS, or the effective value. So it's not taking an average but of this signal, because the average of this signal up here is 0, but it's going to give me some kind of a value somewhere in here ultimately in the end. And this is what your multimeter measures. So it turns out just from the circuit I was showing you on the previous page, that if I'm dealing with RMS values, that the power is going to be I squared R, for example, which is I RMS, the root mean squared value, times R. So this also, well, this gives you the value of the RMS power, which is, of course, the power dissipated in the resistive part of the load. power is also V squared over R, which is going to be the RMS value squared over R. And then power can also equal voltage times current, which will be the RMS voltage times the RMS current. And when you do that, you will find the real power that's dissipated by the load. You will not get a complex answer for this where you have to find the real part of it. You will get the real power that's dissipated by the load. Now, if in this course, of course, we're dealing a lot with sinusoidal or functions, periodic, something that's cosine something. So we deal with current, like for example, being I max or I peak times cosine omega t. And so the question is, what's the RMS value of that? So your book went and did that example for you. So I max squared cosine omega t squared, that's squaring the function. Then you have to integrate it over the period. So to do that integration, use your trig identity right here to split up that cosine squared omega t. And when you do the integration, you'll get that the I RMS equals I max or I peak divided by the square root of 2. Similarly for voltage, of course, you'll get the same. For voltage, of course, you'll get the same thing. So the average power that we calculated before, which was 1/2 the peak current, peak voltage times the phase difference, it turns out that if I substitute in RMS values instead, then we find that the average power is VRMS IRMS times that phase difference. And our other equations also apply here. So doing the RMS will absorb these square root of 2 things that occur. And the square root of 2's are also where that factor of 8 came into play in the denominator in the maximum power transfer equation. So you can apply RMS, the definition of an RMS or an effective value, for any kind of shapes of functions. So here's an example out of your textbook where the shape of the function is this trapezoidal kind of function. You just really have to describe it first mathematically and then apply the RMS equation to it in pieces, and you'll find the RMS value. People sometimes forget in the lab that RMS, that your voltmeter is measuring, the formula that VRMS equals 0.707 times V peak only applies if you have a sinusoidal function. So the RMS value that you'll get is different if you have a triangle wave or different if you have a square wave that you're trying to measure. So the last section in this book is about apparent power and power factor, which I think is a lot of times confusing to people. So we started at the beginning of this section with having our voltage as a function of time and our current as a function of time, and you can express that in phasor notation. And we showed that the average power was this kind of an equation, 1/2 V max I max cosine of the difference between the two phases. And that stemmed from the fact that we multiplied these two cosine functions together and it got a DC or average part, and then it got an AC part oscillating at 2 omega, and the average of that is 0. Therefore, only the DC term that resulted from multiplying these two cosine functions together is what contributes to average power. If you substitute for V max, instead that you substitute the RMS definition, in other words, VRMS equals 1 over square root of 2 times V max. You make that substitution. We also find that average power, or power dissipated in the circuit, is VRMS times IRMS times, again, this cosine of the two angles between the current and the voltage, which you have to keep track of. So this multiplier right here, this cosine of the difference between the two phase angles, We give that a name, and we call that the power factor. So it's really saying, from a geometric point of view, let me switch to my PowerPoint slides. Oh, this is my PowerPoint slide. I thought it was your textbook for a moment. I pasted it in my textbook. Pasted my textbook into there. So what it's really saying, if I were to draw my power as vectors, and if I could draw on my drawing pad and draw a straight line, that would be nice too. So if I draw power as vectors, I have power average is a real power, power dissipated. So this is your power average, which is these equations right here. And there is an angular part of that right here, which is the difference in these two angles right here, the theta phase angle of the voltage and the phase angle of the current difference. So this angle right here is right there, and so this power and this cosine of that to give you the power average is called the power factor. So there's our power factor, and it says how much of this power is real and being dissipated by the real part of the load. And of course we can have a reactive part here, because if you just look at the geometry there, we can have a reactive part in this too. So this part of the power right here, this part of the power is called the apparent power. That's power apparent. And then the average real power dissipated is the cosine of that angle right here, and you get that. The EE213 textbook calls that power true. And then there's a last other part here, which is a power reactive, which is actually really an indicator of what energy is being stored in the capacitive or the inductive parts of the component that you're looking at power dissipation in. If I were to have found power by calculating 1/2, so power average is 1/2 the real part of V, which is a vector, times I complex conjugate, which is a phasor. The real part is this horizontal part of the axis of my plot right there. And the imaginary part of calculating this, the imaginary portion of calculating that, would be your power reactive. If this imaginary part were a plus number, plus imaginary part, power reactive is pointing up. If, of course, the result of this calculation before you take the real part is of the form, if it's, let me say that again, if it's of the form A plus JB, then power reactive is pointing up. If this calculation of multiplying two complex numbers together results in A minus JB, then power reactive is pointing down. And your book makes a point of saying who's leading who, but I thought it was a little confusing, so let's clarify. So when they talk about leading or lagging in this section of the book, they're talking about whether the apparent power is leading or lagging the average power. And you just need to be clear in how you answer the question. If this cosine, if this power factor comes out to be positive, power apparent is leading power average. If that angle is a negative, then power apparent, which will be pointing down then, is lagging power average, or power average is leading power apparent. So you just need to be clear when you answer the questions who's leading and who's lagging. And sometimes it's not clear in textbooks who you're referring to. So lead and lag is a relative. You also have to remember that these vectors are always rotating in a counterclockwise fashion at an angular rate. In power, it's going to be at an angular rate of twice the frequency. Who's leading is who crosses this horizontal axis first. So if these vectors are rotating around counterclockwise, power apparent crosses before power average. And that means power apparent is leading power average. Speaking of whether it's leading or lagging, book likes to say whether the power factor is leading or lagging, which is sort of opposite to drawing your saying whether the power apparent is leading or lagging. So if this turns out to be, it's actually whether the cosine of the angle turns out to be positive or negative. So according to your textbook, the way they treat it. So if this turns out to be, cosine of this turns out to be positive, then that's considered leading in the circuit, even if the angle is negative. Be careful here. Once again, we talk about current leading voltage and voltage leading currents, but we need to be careful when we say that we specify which two components we're comparing, always, because it can be specified more than one way, and the answer in the way your textbook is specifying it is not the only way that leading or lagging can be specified. So just be careful there. Let me be clear. It says in this example in your textbook, they do a calculation. Power factor equals cosine of the differences between these angles, voltage and current. And so turned out voltage was at minus 20 degrees and current was at 10 degrees. So, but you're taking the difference right here, right? And it says it's leading. But who is leading who? Power factor, they say, is leading because current leads the voltage. Can I see that in this equation? Yes, I can. So if I draw my picture, voltage was at minus 20 degrees. So maybe that's minus 20. And current was at a plus 10 degrees, something less. That was current. This was at plus 10. This was at minus 20 degrees. And if these two vectors, phasors, are rotating around at an angular rate, in this case they're going at an angular rate omega, the first one to cross the axis is I. So I leads V. And so they are saying that means that the power factor is leading. I prefer to think of, see, they say power factor is leading, but I prefer to be more explicit because I want to make sure that I understand that current is leading voltage. And I can see that from the relationship of the argument of the power factor right here. The next section, complex power, actually summarizes what I just said. So all of this power talk gets confusing. Am I RMS? Am I average? Am I instantaneous? What am I? So over the years, people have tried to make these relationships more simple. And to me, the simplest thing is to do what we call complex power, and which is our expressing everything in complex numbers, because then it gives you all the information that you ever need to know about what total thing is happening at the load. And I don't know why they said parallel loads, because it applies to any loads here. So complex power is really important because it contains all of the information about the load. So here's the calculation for complex power. So these are V's that are maximum vectors, phasor notation, right? And if we take just the real part of that, that's the average power. We can also have this formula right here with RMS values. So these two, the top one, first one and the second one, are equivalent. And in that picture I just drew on the previous page, I drew what power looks like. Power looks like something like this. I have a complex power right here, which is called your apparent power. And if I just take the real power part of that down here, the real part of that is your average power, or the part that's real and dissipated by the load. Power average is now given this term P right here in this section. And Q, or the quadrature meaning it's in one quad of 360 degrees, or it's orthogonal. Quadrature usually means orthogonal, is your reactive power. So this is, the P is also called true or real or average power, since your textbook gives you all of those things. The power that's the quadrature component is also the reactive power, which can be either capacitive or inductive. And that's the imaginary part of S. And then there's S, which is PP plus or minus JPQ, which is your apparent. That's your apparent power. These are all of the words going around. So if there is no quadrature component, Q equals 0, or there's no imaginary part of the complex power, then you're talking about a purely resistive load. If Q is less than 0, so it's something that points down, your apparent power is pointing down, then that means it's a capacitive load, and we call that a leading power factor. And I showed you on the previous slide how that comes into play by looking at the two angles. And Q greater than 0 is for an inductive load. So this is the quadrature component of power, or the reactive component of the power, and it's not really a true power because those components that are reactive do not dissipate any power. They may store some energy, but they don't dissipate any power. So I hope that clears up the plethora of terms in this section. So here's kind of a summary picture of all of that I was just talking about. So P is real or average power. Q is the reactive part, or the quadrature power component, and S is apparent power here. And we can make a triangle out of that, and that angle that occurs here, this angle, turns out that also if you are doing an impedance triangle, that angle is exactly the same angle. So if you find the total impedance of the circuit, find the angle of that, you get the same answer. So if X is positive, it's a capacitive circuit. If X is negative, it's a if X is positive, it's an inductive circuit. If X is negative, it's a reactive circuit. I mean a capacitive circuit. So here we say positive Q is a lagging power factor, and negative Q is a leading power factor. But you have to again relate it to who's leading or who's lagging. So lagging power factor, lagging power factor shows that I just did it in a previous slide. Was it this slide? No, 2 slides ago. This one. So this says it's a leading power factor because V is down here, I is at plus 10, I is leading V, so they called that a leading power factor. And that's what would occur in a inductive load. That is true. Q would be greater than 0 in an inductive load. So that is true, correct. Inductive points up, capacitive points down. So that is true. Lagging power factor, leading power factor. So this is what power engineers like to use. They like to use these leading and lagging terms. So that's how I guess I could say it all ties together at this point in time. Leading and lagging continues to always be confusing terms, but you have to draw, if you draw these vector diagrams and see exactly what it means, then you can figure out who's leading or lagging who. if you don't remember it by a definitional type thing. I think that's the end of this this chapter, except for the optional sections, which I don't think we need to do. I think the most difficulty in this part of this chapter is really the fact that you have to keep track of all these complex numbers, and the textbook likes to mix up the angular versus the trigonometric versus the complex representation of all of these quantities in a circuit. Other than that, you are applying your Kirchhoff's laws as you already know them for loops and meshes. You're just having to keep track of the math that's involved there, and whether you're using peak values, RMS values, or yes, peak values or RMS values when you do your equations.